First of all, we need to build the MNIST example for the autoencoder structures, okay? In order to do that, we need to import the torch, import torch nn as nn, import torch optim as optim, and import torch vision transform as transforms. From torch vision import dataset. This dataset contains the many general data in order to test your NN algorithm or the machine learning algorithm, guys. Okay, and so the from torch utils data import data loader in order to load your data in here, and matplotlib pipe load as the result demonstration. First of all, we need to set a device in here. Torch device Judah is assigned in here. Okay, using device is the device. Okay, this is the GPU utilization guy. Okay, so you can speed up your training process based on these informations. And so the autoencoder can be built in here just like this one. The class autoencoder it's derived from the NN module. So just the NN. Okay, so we need firstly the super should be called in here. I'm sorry, def init function should be built with the super autoencoder self must be called in here, just like this one, the init. Okay, and after that the self encoder can be built with the NN sequential form these terms. Okay, and so this sequential can be built with the many neurons, and the sigmoid function or the activation function or dropout layer can be built in this sequential layer. For example, 28 times 28 is the input data, 128 neurons in here. After that we can apply the rel layer in here, and also NN linear can also be implemented 128, because the 28 is the output, this is the input, and so 64, and NN relu should be used in here as an activation function, and NN linear 64 12. Okay, and so NN relu and NN linear is called with the 12 and 3. And here this is the compressed representation, guys. Okay, and so we have three main features must be learned from this dataset. Okay, after that the self decoder is built with the same structure, sequential. Okay, so NN linear 3 12, and then relu is given here as an activation function, and then linear 12 64, this is totally symmetric. Okay, and then linear 64 to 128, and then relu is here, and then linear 28 and 28 times 28. Okay, after that we need to give the NN sigmoid formula in here, just like this one. Okay, because this generates to the what output 0 to 1. Okay, So in order to implement these algorithms in here, and so we need to write the forward self and x is the overridden of the main nm module cases. Okay, and so x self encoder x is given in here, and x self decoder is given in here. This one, the second one, or just the theta. Okay, so just the theta, and after that the x is assigned and return x in this case. So here load and prepare dataset and transform can be built with the transforms that compose is a specific function to build the what are transformation methods in here. Okay, first of all we need to set the tensor in here, and also transforms lambda expression can be used in here. Lambda x input torch flatten is applied hold the data, and so we can build these lambda functions or the transform functions in order to what? In order to apply our dataset. Okay. After that, train dataset is built. The datasets mnist, and so the root is equals to the what dot data and train true, and download if doesn't true, and transform is equals to what the transform. See, this application is applied in these nominations, and so the train dataset can be obtained just like this one. Okay, and after that the train loader is utilized for the what? For the batch learning and the episode learning. Okay, and so if we want to train this neural network, this the raw data, and so this must be loaded to the what? The data loader, guys. Okay. Just like this one, train dataset, batch size 64 for example, and the shuffle is the true. Okay, so firstly I need to copy all of these algorithms in here, or we can write this times. Okay, and so the mnist is automatically downloaded from the what? From the basis. Okay. Just like this one, just see that. I'm sorry, that's the module. See, these are the dataset downloading from the what? Automatically from the mnist. Okay, it's the number dataset. Okay, and after that we have the whole data with the label of this one. So loss optimizer and model should be defining here. The model autoencoder constructor code and to device to what? To utilize of the what? The GPU. Criterion is defined with the NN MSE loss, and optimizer is built with what? Optim Adam. So the model parameters should be given in here. LR rate is equals to 1e minus 3, and also we need to give the betas in here just like this one, 0.9 and 0.999 for example. This is the Adam optimizer. Okay, so training loop can be built with what? The num epochs is equals 10, and for epoch in range of num epochs, so the model train is opened in here, and running loss should be defined for image and translate parameter in train loader should be utilized to what? To batch learning, just like this one. And so emgs is equals to emgs to device, this is the GPU utilization, and so the outputs should be defined with the model MGS, and loss is assigned the criterion with the what? With the outputs and the EMGS. Okay, that's the loss criterion. And after that, the optimizer 0 grad should be resetting here, and loss backward is prepared, and optimizer step function is given here. And also the running loss is increased with what? The loss item function times image size of 0. After that, the epoch loss can be with running loss with what? Len train loader dataset. Okay, this is the epoch loss. After that, we need to with printf epoch of the what? Epoch plus 1 divided by num epochs. Okay, and also the loss is equals to what? The epoch loss for okay. This is the training class. Evaluation and visualization can be built with the what? With this one. Model eval should be called in here. Data iter is defined the iter train loader. Okay, because this iter is just like the pointer, and so at each case this data iter is giving the next part of this image. Okay, and so the images next is a function data iter. Okay, so image equals to the image to device should be given in here, and with torch no grad, it's not a training class. Okay, and so reconstructed can be built with what? The model image. Okay, just like this one. So this is the what? Testing the R algorithm. The reconstructed must be equal to what? The real images. Okay, and so the images tensor moving CPU, in order to visualize the R program in here, just like this one, image CPU should be viewed as -1, 28, and 28. This is the picture format, and reconstructed is also assigned with the reconstructed CPU, and this is the same, just like this one. Okay. So the display operation is simple, and so I can copy all of these terms just like this one. For the subplots 2 and 10, we have the 10 numbers 0 to 9, and so at each case the real one and the reconstructed one is taken in here. Okay, so if I run this code then, and we have no error, okay, this value is wrong. And we will wait to train. And after that, these are the results. This is the real image and this is the generated one. This is the real, this is the generated, real generated, real generated, real generated. But there is some mistaken values in here, just like this one. Just see that in the first place, this is the exact representation of the R dataset, but this the reconstructed. The reconstructed is filtered. See, this is the blur values. This is the sharp, but this is the blur because we filtered the whole noisy dataset in here. But the performance is not good enough in here. First of all, we can change the betas in here, just like this one. Just the Adam optimization. This may be good or not, we don't know right now, or we should change the bed size of the R dataset. Okay, but we need to test it. Okay. We're waiting. This is the second representation of this dataset. This is somehow good with the previous case, but the loss function is not changed in here, and so we need to take this back. But just see that we have the three features in here. What about this one is equals to the what? 10. Okay, and so we have 10 main features in here. Maybe this increase the what the representation rate of the R algorithm, because we have 10 different numbers in this dataset. So what happens if I change to this algorithm right now? Okay. See, the loss function right now is more lower than the previous case. Okay, maybe is the 10 main features are suitable to represent the whole data. See, this is more good, right? But in this case, we can generate the whole data, and also we obtain to the what to the main features at what at the latent space of this dataset. Okay. This is just like the variation of the input for a given dataset, especially for the language translation. These autoencoder structures are mainly utilized because for a given English word, I am a student, ben öğrenciyim, and so this I am a student can be converted into the what into the another dimension with the same number, same representative, right? And so if I put the English words, and so we will have the Turkish one. We can utilize the autoencoders for this case. Okay. Any question? Okay, and so this is the standard neural network structure, but we can also build the CNN one for this case. CNN autoencoder. Okay. So this must be same, and also this must be same, but the rest of them should be removed in here, just like this one. Okay, and so CNN autoencoder can be built in here with the what? Class CNN auto encoder, the derivation of the NN module, it's given in here, def init, which is this one, okay? And so the self is built, the super must be built with the super and self, and the init also given in here, okay? So in order to build the CNN autoencoder structure, self encoder and then sequential is created with what the NN cone 2D. Just remember the R example 1, 16 and 3, and stride is assigned 2 and padding is assigned 1, okay? And so the general calculation 1, 2, 28, 28 is going to 16, 14 and 14 right now, and then ReLU here, okay, comma, and also and then cone 2D is the what, 16, 32, 3, and stride 2, and padding is the 1, okay? And so at the end of this code 32, 7 and 7 is generated, and then ReLU here, and after that the NN flatten should be called in here in order to represent the one-dimensional data coming from the pictures, and after that NN linear 32 times 7 times 3 features in here, okay? And so this is the three main latent variables are given in here, okay? Now the self decoder can be built with what the NN sequential form of these terms. The NN linear should be called in here 32 times 7 times 7, okay? And then unflatten the data 1 and 32, 7 and 7. This is three-dimensional data, three-dimensional matrix. In here it's converted, and so NN cone transpose 2D should be called in here. This is the symmetry of the cone 2D form. 32, 16, 3, and stride is equals to 2. The padding is equals to 1, and output padding is 1, okay? And then ReLU must be called, and then cone 2D transpose 16, 1, 3, the stride 2, padding 1, and output padding 1, okay? And after that NN sigmoid should be called in here, okay? So def forward must be overridden based on this one, x self encoder x, or this can be assigned to theta in here, okay? And x is equalized to self decoder theta. This x is not this x, or this is the y. Here the return y, okay? So in this case we should copy all of these terms in order to gain take times, okay? This the tensor should be assigned in here just like this one. Dataset mnist root data transform through and loader, okay? And this one is the CNN autoencoder, the model in here, the betas in here, and okay. So the rest of them same, okay? So the num epoch training algorithm, num epoch 10 and 4 epoch in range of num epochs, model train should be opened, and for batch idx and image data in enumerate of the train loader should be given in here. This is the split factor of these terms, and after that the image equals to the image to device. Output of this model is the image, and the loss can be calculated with the criterion, okay, with the what, output, and image. After that the optimizer gradients must be reset 0 grad. Loss backward error is calculated, and optimizer step should be called if batch idx percentage 100 must be equals to 0 if the equals to 0, and so the print f epoch is equals to what? Epoch plus 1 divided by num epochs, okay. This one is the 1 hat, and after that we need to write the batch also in here, batch idx and len train loader, okay. And also that's the batch. This is the loss, okay. The loss item is given by loss item dot for f, okay. So in order to visualize the and test the algorithm, model eval is called data iter is defined with the same way in the previous case, and image next can be called data iter. So image equals to the image to device, and with torch no grad output equals to the model image, okay. After that image CPU is set with the image CPU in order to visualize the R dataset, okay. And also the outputs CPU is equals to the outputs CPU. Rest of the algorithm is the same with this one. So if you run this code, there is no error. And then the R algorithm is trained to the neural network, the convolutional neural network, okay. Say for given 3 latent space feature, these are the results for the convolutional neural network. And so firstly we need to change the learning rate and the betas in here, just like this one. For this one, this must be assigned to the 500 guys. We're waiting. Allah Allah. See, in this case, we will reach the total error at the what at the 0.039. This is not good. And so, it must be taking the rest, the 9. But we need to change to the 10 main latent variables in here. 10. After that, this must be 10. Right now, see, the loss is hugely lower than the previous case, guys. This is highly effective to find out to the what? To the correct number of your latent space here. Okay? Right now, see, this is more good than before, right? It's highly reconstructive in this case. What about this one? If the betas, the gradient is updated with the what instantly by selecting the first parameters of the what of these ones. What's the result of this code right now? See, we cannot learn highly effective right now, guys. 0.02. See, it's not good for our case. In the real-time control algorithms, we need to set the beta's first parameter the lowest. But maybe in this approach, we need to hyper-optimize these parameters. See, it's good, but not enough. So the last case, we can assign 99 and 9999. In here, this is the last example. We need to decide which one is good or not for our cases, right? And so we don't have any rules for selecting the learning rates or the betas for a given dataset. Yani arkadaşlar sizin burada verdiğiniz parametreleri, beta'yı, learning rate'i hepsini optimize etmeniz gerekiyor. Belki ben bet size'ı 32 yapsam burada bu daha iyi çalışacak ama belki de daha iyi çalışmayacak. Bu tamamen sizin kullandığınız veri setiyle alakalı. Bunu hiç unutmayın. Okay. Any question?